Electricity. Electricity is really important in today's world. It is a useful and easy to control type of energy that we use in homes, schools, hospitals, industries and more. This is an electric cell. This is an electric wire. This is switch. And this is an electric bulb. This arrangement is called an electric circuit. A continuous and closed path of an electric current is called an electric circuit. If the switch is in off position, the circuit is not complete. When the switch is on, the circuit becomes complete and the electricity starts flowing in the circuit. This flow of electric energy in the circuit is called electric current. The direction of the flow of electric current can be described in two ways: conventional current and electron flow. Conventional current. This is the direction in which positive charges would flow. By convention, it is defined as flowing from the positive terminal to the negative terminal of a power source. This convention was established before the discovery of the electron and is still used today in most circuit diagrams and descriptions. Electron flow. In reality, electric current in a conductor, such as a metal wire, is due to the flow of electrons. Electrons are negatively charged and move from the negative terminal to the positive terminal of a power source. This is the actual physical flow of electric charge in most conductive materials. Now let's see how is the electric current expressed. Electric current I. The current through a conductor is the amount of charge Q that flows through it in a given time t. It is given by the formula I equal to Q by T. I means electric current, Q means electric charge, and T is time. Let us see the units of electric charge and electric current. SI unit of electric charge. The unit of electric charge is the coulomb, C. 1 coulomb is roughly equal to the charge of 6 into 10 to the power 18 electrons, with each electron carrying a charge of 1.6 into 10 to the power of minus 9 coulombs. SI unit of electric current. The unit of electric current is the ampere, A. 1 ampere is the flow of 1 coulomb of charge per second. 1 A equal to 1 C by 1 S. Smaller units of current. Let's see the smaller units of current. Milliampere is equal to 1 MA equal to 10 to the power of minus 3 angstrom. Microampere, mu A. 1 mu A equal to 10 to the power minus 6 amperes. Then how do we measure the electric current in a circuit? Ammeter is an instrument used to measure electric current in a circuit. It should be connected in series with the circuit components. Electric potential and electric current. Electric potential and electric current are fundamental concepts in electricity. First, let us understand electric potential. Here, two water tanks are connected and they both are at the same level. Now, can you see any movement of water from one tank to another one? No, because the potential energy of the water in both the tanks is same. But here in this case, the water in tank 1 flows to tank 2 because the potential energy of water in tank 1 is higher than the potential energy of water in tank 2. That means the water flows due to the difference in potential energy of the two tanks. Tank 1 has higher potential energy than tank 2. So the water flows from tank 1 to tank 2. In the same way, a potential difference exists between the positive and negative poles of a cell. So, the flow of electricity takes place between one pole to another. This flow of electricity powers the things like light bulbs, fans, etc. So, potential difference is the difference in the electric potential energy between 2 points in a circuit. Now let's see what is voltage. Voltage is simply another word for potential difference. When we measure the potential difference between 2 points, we measure it in units called volts. That is why we call it as voltage. The SI unit of electric potential difference is volt V. It is named after an Italian physicist, Alessandro Volta. So 1 volt is equal to 1 joule by 1 coulomb. 1 V equal to 1 J C to the power minus 1. So 1 volt is the potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. The potential difference is measured using an instrument called a voltmeter. The voltmeter is always connected in parallel to the points between which the potential difference needs to be measured. Next, electric current. Electric current is the flow of electric charges through a conductor. If we go back to our water tank example, electric current is like the flow of water through a pipe. The amount of water flowing per second is similar to the amount of electric charge flowing through a wire per second. Electric current is measured in amperes. Example, when you turn on a light switch, you create a path for the electric current to flow from the battery through the wires and into the light bulb, causing it to light up. The flow of electric charges, that is the current, which powers the bulb. So, electric potential is the pressure that pushes the electric charges, and electric current is the flow of those charges through a conductor. So this is about electric potential and electric current. Electric circuit diagrams. An electric circuit generally includes a cell or battery, a switch or plug key, electrical components, and connecting wires. To make it easier to understand, we often use a schematic diagram where the different parts of the circuit are represented by standard symbols. Now let us see the important electrical components and their standard symbols. This is an electric cell and this is its symbol. A battery or combination of cells and its symbol. Plug key or switch open. This is the symbol of it. Plug key or switch closed. This is the symbol of plug key closed. This is a wire joint and this is the symbol of it. Wires crossing without joining and this is its symbol. Electric bulb and this is its symbol. A resistor of resistance R and this is the symbol of resistance. Variable resistance or rheostat and this is the symbol of it. Ammeter and this is the symbol of ammeter. Voltmeter and this is the symbol of voltmeter. By learning these symbols, you will be able to understand a diagrammatic representation of an electric circuit. Ohm's law. In 1827, a German physicist, George Simon Ohm, proposed a law that explains the relationship between voltage, current, and resistance in an electrical circuit. Voltage V is like the push or force that makes electric charges move through a circuit. Current I is the flow of electric charges through the circuit. Resistance R, it is the property of the conductor to resist the flow of charges through it. Means resistance slows down the flow of electric charges. Ohm's law states that the current I in a circuit is directly proportional to the voltage V and inversely proportional to the resistance R. In simple terms, if you increase the voltage, the current increases. If you increase the resistance, the current decreases. Mathematically, Ohm's law is written as V equal to I into R or I equal to V by R, where V is the voltage, I is the current, and R is the resistance. So if you know any two of these values, you can calculate the third one. Let us see how to verify Ohm's law with lab setup. To verify Ohm's law, we need few cells, a cell holder, a conductor, and an ammeter to measure the electric current, and an voltmeter to measure the potential difference or voltage. Now connect the circuit and place only one cell in the cell holder. Let us note down the readings in the voltmeter and in ammeter. Write these values in a table. Now, let us add one more cell to the battery and note down the readings. Take the readings with 3 cells and next with 4 cells. Now let us observe the table and the values recorded. Now plot these values on a graph having current flow on x-axis and potential difference or voltage on y-axis. With one cell, the current value is 0.15 and voltage is 0.3. And with two cells, the current value is 0.25 and voltage is 0.5. With 3 cells, the current is 0.375 and voltage is 0.75. With 4 cells, the current is 0.5 and voltage is 1.0. So we have plotted these values on the graph. Now the VI graph has a straight line passing through the origin, which indicates that V is proportional to I, or V by I is constant. What is that constant? That is nothing but resistance R. So V by I equal to R. V equal to IR, or we can write I equal to V by R. Now let us know some more details about resistance. The SI unit of resistance is ohm. It is represented by the Greek letter omega. If the potential difference across two ends of a conductor is 1 volt and the current through it is 1 amperes, then the resistance R of the conductor will be 1 ohm. That is 1 ohm equal to 1 volt by 1 ampere. If the resistance increases, the current passing through the conductor decreases. If the resistance is doubled, the current becomes half. Sometimes it is necessary to control the current in a circuit without changing the voltage source. In this situation, a compound called variable resistance or rheostat is used to adjust the current in a circuit. Rheostat is commonly used in electric circuits to change the resistance and control the current. Resistance and resistivity. Now let us understand more about resistance. Why do conductors show resistance? The flow of electric current through a conductor is due to the movements of electrons. Electrons in a conductor aren't completely free. They are attracted by the atoms in the material, which slows down their movement. This slowing down of electrons is what we call resistance. Resistance opposes the flow of electric current. Different materials have different resistance. Here is a broken circuit. Now let us close this circuit with different types of materials and check the amount of current flow in each case with the help of an ammeter. Let us close this circuit with wire A and note down the readings in the ammeter. Now change the wire A with wire B. In case of wire B, less current is passed compared to wire A. This can be observed in the ammeter. Now replace wire B with wire C. In case of wire C, very less current is passed compared to wire B. Now replace the wire C with wire D. Now there is no electricity passed in the circuit and no readings is observed in the ammeter. So from the above experiment, we can call wire A is a good conductor. What is a good conductor? A material with low resistance and allows the electric current to flow through it easily is called a good conductor. Now wire B, we can call it as a resistor. What is a resistor? A material with some resistance but still allows the current to flow. It is called a resistor. Next, wire C. And we can call wire C as a poor conductor. What is a poor conductor? A material with higher resistance allows less current to flow is called a poor conductor. And wire D is an insulator. Insulators have very high resistance, which makes it extremely difficult for electricity to flow through them. Now let's see the factors on which the resistance of a conductor depends. Resistance of a conductor is dependent on the following factors. 1. Length of the conductor. The resistance of a conductor increases as the length of the conductor increases. 2. Cross-sectional area of the conductor. The resistance of a conductor decreases as the cross-sectional area increases. And the third one, nature of the material. The resistance of a conductor also depends on the type of material it is made from. So, Resistance is directly proportional to the length of the conductor. That means the length increases, the resistance also increases. Resistance is inversely proportional to the cross-sectional area of the conductor. That means the cross-section increases, the resistance decreases. The resistivity ρ is used in the formula that relates the resistance R of a conductor to its length L and cross-sectional area A. R equal to ρ into L by A. In this formula, R is the resistance, L is the length of the conductor, A is the cross-sectional area, and ρ, resistivity, shows how much the material itself opposes the flow of current. The SI unit of resistivity is ohm meter. Resistivity is unique property of each material that shows how much it resists the flow of electric current. Metals and alloys have very low resistivity, usually between 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter, making them good conductors of electricity. Copper and aluminum are the pure metals commonly used for electrical transmission lines because they are excellent conductors with low resistivity. Tungsten is a pure metal used for making filaments in electric bulbs because of its high melting point and durability. Alloys generally have higher resistivity than the pure metals they are made from. If alloys have more resistivity, then why are they still used in electrical devices? Alloys are resistant to oxidation at high temperatures. That means they do not burn even at high temperatures. That is why they are often used in electrical heating devices like electric irons and toasters. Insulating materials like rubber and glass have very high resistivity, ranging from 10 to the power 12 ohm meter to 10 to the power 18 ohm meter, making them poor conductors of electricity. Both the resistance and resistivity of a material can change with temperature. Resistors in series and in parallel. In certain complex circuits, more than one resistor may be used. They may be arranged in series or in parallel combinations. Let us see the differences between resistors in series and in parallel. Connection type. In series, resistors are connected end-to-end, forming a single path for the current to flow. In parallel, resistors are connected across the same 2 points, providing multiple paths for the current to flow. Current flow. In series, the same current flows through each resistor because there is only one path for the current. In parallel, the current divides and flows through each parallel resistor with different amounts of current depending on the resistance of each path. Voltage distribution. The total voltage across the series combination is the sum of the voltages across each resistor. Each resistor has a different voltage drop. Whereas in parallel, all resistors in parallel have the same voltage across them, equal to the voltage across the entire parallel network. Total resistance. In series, the total resistance is the sum of the individual resistances. Rs equal to R1 plus R2 plus R3. The total resistance increases as more resistors are added in series. In parallel, the reciprocal of the total resistance is the sum of the reciprocals of the individual resistances. 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. The total resistance decreases as more resistors are added in parallel. Effect on circuit. Increasing resistance by adding more resistors in series results in a lower current for a given voltage. Adding more resistors in parallel lowers the total resistance and increases the current for a given voltage. Heating effect of electric current. When an electric current flows through a conductor, it encounters resistance. This resistance causes some of the electrical energy to be converted into heat energy. That means, due to resistance in a circuit, certain amount of electric energy is converted to heat energy. This phenomenon is known as the heating effect of electric current. For example, a fan running for a longer period becomes hot. Certain electrical devices are made with materials that have more resistance and produce large amount of heat. For example, electric iron. Joule's law of heating. Joule's law of heating explains how electrical energy is converted into heat energy when an electric current flows through a conductor. This law is important for understanding the heating effect of electric current. Joule's law states that the heat produced in a conductor by an electric current is directly proportional to the square of the current passing through the conductor, the resistance of the conductor, the time for which the current flows. That means H equal to I square into R into T. If the current flowing through the conductor increases, the amount of heat generated also increases. This is because more electrons are moving through the conductor, leading to more collisions with the atoms, and hence more heat is produced. Higher resistance, higher heat means when the conductor opposes the flow of current more strongly, it leads to more heat generation. The longer the current flows through the conductor, the more heat is produced. Applications: electric heaters. The principle of Joule's law is used in electric heaters where the electrical energy is converted entirely into heat to warm a room. Electric iron. In an electric iron, the heat produced by the current is used to press cloths. Fuses. In electrical circuits, fuses are designed to melt and break the circuit if the current is too high, preventing damage. This melting is due to the heating effect described by Joule's law. Thanks for watching. Please like the video. Please share this video with your friends. Please subscribe to Grade Booster channel. Press the bell icon to get all the latest updates. Check the description to find links of other useful